right, well, good morning, everyone. First of all, I would just like to acknowledge the traditional owners of the land on which I am, which is the Wurundjeri people of the Kulin Nation down here in Melbourne, acknowledge their elders past, present and emerging, and also acknowledge the traditional owners of the lands that you all are on, and note that these lands were never ceded. So it's my great pleasure today to introduce Professor Sander Greenland to give us a talk. But just before we do, I just want to also encourage those of you who are attending the seminar today but who are not AEA members to consider joining the society. We do usually offer an annual scientific meeting and local seminars and events. Obviously, those events haven't been running in the same way they normally would in the last year. We were also supposed to be hosting the World Congress of Epidemiology here in Melbourne last year. Again, that didn't go ahead. However, it is going ahead this year, and places are filling up fast for the workshops, and it would be great if you could register your interest, and perhaps Alison or Bridget can put in the chat the URL for the Congress. We also have with us here today the president of the AEA, Dr. Bridget Lynch. So it's a great pleasure that I'm introducing Sander. So when I was a student at UCLA, I was fortunate that Sander was still actively teaching, and me and my classmates would go to his lectures with our little MP3 recorders. Our phones didn't have that capability then, and take copious notes, and then spend hours afterwards trying to decipher what on earth it was he was trying to tell us. But it wasn't just the students at UCLA who have benefited from Sander's wisdom. He's made tremendous contributions to epidemiology during his career, written many hundreds of papers, co-authored the textbook Modern Epidemiology, which many of us used in our learnings. And as one colleague described to me, has generally kind of policed epidemiology for the last few decades to make sure that we're actually doing things in a valid way. And that's consistent with today's topic, which is an issue that Sander's been spending a lot of time on, particularly since he retired, which is trying to ensure the valid use of statistics in epidemiology and health science. So I'll hand it over to you, Sander, and I guess the rest of us can turn our cameras off, unless you want us to leave our cameras on while you're speaking. Let us know, but over to you, Sander. Thanks very much.
All right, thank you for having me, and the nice introduction. Well, I'm not doing anything terribly new here, except just another revision upgrade. And I'm going to try and speed through what is several hours worth of slides here, trying to emphasize other points and a few new slides and examples on this general theme, which I've talked about under various names, as you can see on this slide. Some time ago, quite some time ago, around the time I was retiring from UCLA, I said to colleagues, I said, epidemiology is doing well. This is an epidemiology meeting, and usually I'm talking about this to a more general audience or statistics audience, where I'm really beating on statistics, and I still will. But I said I'm going to pay more attention there because that's the source of a lot of the problems that I see in epidemiology. And the biggest problem, I see this in medicine too, but it's a real big problem in medicine. And most of my work, my applied work, has been in medical epidemiology and looking at drugs, devices, practices. And it's terrible to see how people have been hypnotized into extraordinary levels of deception, cognitive, just irrational cognition based on what they were taught in statistics. And I came to realize that the people teaching them suffer much the same. And it's something very strange sociologically had happened. And I still ponder it. And that is some kind of statistics has become at least a large segment of, particularly in medicine, has become a kind of social control movement, which mandates a certain kind of approach to data, which is more along the lines that you'd expect of artificial intelligence, saying, well, we have customers, people who don't want to have to think too hard. They just want formulas to pump through. And then we'll give them that. And of course, I'm sure you've all seen many weird consequences of that. But I think epidemiology is in much better shape than most fields that I'm familiar with, because through the efforts going back to Ken Rothman, starting in the 1970s, beating very hard on a lot of these problems, seeing them. But this is how my view of things about statistics, this old saw about science progresses funeral by funeral. But I say in statistics, authority seems to be immortal. There's a heroic narrative about science progressing by each generation, challenging ideas of its predecessors and discarding those that fail stringent empirical tests. In contrast, the statistics is decayed by enshrining traditional methodologies and then defending them by academic, mathematical, and philosophical appeals, along with underplaying harms to public information. What do I mean by harms to public information? There's a recent figure that I love that shows the cratering of knowledge produced by the use of the 0.05 criterion, not only for publication, but also driven by what the authors want to conclude. What you can't see here, but Van Zwet kindly supplied in more detail, is the data right there at the 0.05 boundaries, those two little tick marks there. If you split that up, you would see that there's a pileup on both sides of 0.05, and I'll show you examples of that later. There's more people trying to get just above 0.05, but there's quite a few trying to get just below. So we end up with statistics basically giving its blessing to cognitive biases, in fact, encouraging them as scientific principles. And I'll talk about those, the treatment of mathematical frameworks as physical realities, neglect of human biases. This is a problem with much teaching in almost all fields. People are blind to the biases that they have, and this has rotted the core of statistics. Now, a solution that I've been promoting for years now is reconstruct statistics as information science, not a branch of probability theory. And that can get a little technical, but the important point for epidemiology is, do you have cognitive science and causality theory as core components? Well, causality theory has become a core component of at least epidemiologic teaching, plenty of articles, and in a lot of statistical methods too. Throughout epidemiology, economics, and other fields, it's spreading, but not so much for cognitive science. And I think that that's even more important, I'm believing. And the important point is that one important point is that there's one view of probability, which is a legitimate view. It's not the most popular, but it's been around for a long time, is that these probabilities are just subjective bets that people have, and we reify those. We see causal explanations for patterns we recognize by considering highly non-random selection of a few causal possibilities that we think of or that people put forth. And then we dump all the rest, the residual infinitude of the causal explanations we didn't even imagine, as into some metaphysical cause called chance. Now, one way of trying to approach these difficulties is to make sure we view all analyses as part of a vastly incomplete sensitivity analysis. Now, this is really important for epidemiology more so than, say, the parts of statistics dealing with small experiments where randomization is successfully enforced. And when we do that, we see that there's a lot of the splits, the philosophical arguments in statistics aren't very relevant, in my view, for what we really confront, especially when we're talking about the COVID pandemic or any sort of situation where we have to rely heavily on observational data. And it's because the schools that statistics fractionated into in the last century, starting a century ago, didn't cover the causal or contextual dimensions or the problems of cognitive issues. And what unifies inference concepts is not probability, but causation. We talk about past causes, what explains our observations. That's what we as epidemiologists, I think, are doing better than a lot of other fields, because we're, to a great extent, accustomed to this, saying what are the different explanations for these patterns. because we can't fall back on the magic bullet of randomization or even random sampling to try and come to some conclusion. And this means asking about the physical mechanisms, not abstractions of their behavior, such as probabilities. One of the many, many crazy things I see in statistics is that they'll talk about probability models as the treatment assignment mechanism or the sample selection mechanism. Those aren't mechanisms. Mechanisms are physical things like the physician, even in a randomized trial, the physician doing the random assignment and possibly messing up with it or even cheating. And then, of course, we're concerned with future effects. How will our actions affect the future? That's asking about how to change the behavior of real physical mechanisms, actual event frequencies, not probability distributions. So any reform that we attempt that retains selective reporting based on study outcomes will distort the distribution of available outcomes relative to the total. We see this happening from the standard 0.05 statistical significance criterion, but a point that other statisticians like Andrew Gelman has said, this is a problem that we'll get this distortion of the literature anytime we select on outcomes. And we know that as epidemiologists today, modern epidemiologists, we know about causation, and we know if we're selecting people based on outcomes, we better be able to take account of that in some very detailed way, or we'll get a messed up sample. We are messed up analysis. It'd be like computing rates from raw case control data. Now, one of the problems is that statistics has even encouraged the confusion of inference, scientific inference, with this thing called statistical inference. But inference, it's a good example of many of the words, common English words that statistics hijacks and then forgets about all the rest of its meaning. And an inference is a conclusion on the basis of evidence and reasoning. And scientific inference is a complex, narrowly moderated judgment. And we know in epidemiology, another thing I think I've seen epidemiology, or at least the leading journals, as being very good at is moderating judgment about what's going on. Again, because they can't fall back on magic randomization, as it were. But notice this little diagram at the bottom. The idea is that reality causes your perception, it causes my perception, but those are separate things. Obviously, our perceptions are different. All you have to do is look at people fighting about things. This is what makes inference part of cognitive science. If you contrast that to statistical inference, it's all that's become is taking output from data processing program, which is a learning algorithm, and generating so-called inferences via decontextualized rules, such as declare that there's no association because P was greater than 0.05. And this is still standard enforced by JAMA, for example, so-called leading medical journal, which is basically a drug industry journal. It converts oversimplified models of mechanism generating data, the causes of the data, into these abstract probability distributions. And the semantic void it leaves causes inferential errors and facilitates deception. And the problem, part of the problem is that statistics ignored or denigrated semantics and ordinary language, favoring instead deceptive jargon, promising significance and confidence, even when studies provide nothing close without huge leaps of faith. And this is all done to sell technical products and services based on dense formalisms, dense notation, artificial precision. See this consistently. These assumptions and dangers are beyond most users and consumers in the soft sciences. I know from experience, it's most of the users of statistics that don't really have that good an idea of what all the assumptions built into those models and the programs involved. And there's a parallel here with medical product sales. I've started to realize this is the same thing we see in any problem in medicine, including sales reps. And of course, it's not like we were innocent. The scientific community eagerly contributed to this degeneration. Rules that were apparently successful for narrow automated environments, production lines, induce destructive feedback loops in teaching and research because students want explicit practice rules to memorize, to get correct answers. Instructors want ease of grading. I know that very well. Researchers want rules for submitting acceptable reports, and reviewers and editors want to ease reviewing and publication decisions. And the prevailing rules became especially popular and destructive via enforced dichotomies that make things even simpler and satisfy human drives for definitive conclusions, because they imply even when the study is incapable of forcing such conclusions if critically scrutinized. Of course, except for the more research is needed, which is not always justified. So that left that degeneration of statistical science, left a collection of mathematical skeletons, and it left behind explication and training and essential components of scientific inference. How causal networks, not probabilities, produce data, inferences, and decisions. How cognitive biases, as well as procedural problems, enter those causal networks. You look at causal diagrams. The one thing, our use of them, my teaching of them, everybody so far, has been in a very primitive stage where we don't have all the cognitive biases entering. And then how valuations, the motivations, the goals, the real costs and benefits affect cognition and are implicit in all the methodologies. Those aren't in the diagrams in all our causal models anyway. So as I said, the main problem of p-values will extend to any statistic because they stem from truth subverting or perverse incentives and cognitive biases, not from p-values. P-values have become the scapegoat, like some despised minority, for problems they didn't create. The statistics community and the users and the whole scientific community created those problems. And then they figure out all these ways to blame p-values. And in the end, I figured out this isn't the p-value's fault. Again, somebody agrees with me, Andrew Bellamy added a note saying this is not the p-value's fault. Perverse incentives create these cognitive biases, wishful thinking, mind projection to see what incentives dictate, and those biases pervade reports in medicine. Perceptions are also currently manipulated to see incentives for positive reporting while ignoring incentives for negative reporting. Yes, that's going on. There is manipulation. Reasoning motivated by commitment to past teaching, past practice, and financial stakes drives resistance to serious reform. The resistance I'm getting now is getting more traction and getting more spread thanks to the internet and giving a lot of Zoom talks along these lines. It's interesting to see and find out and know about the backstories in some of the resistance. Example, here's a common label on dairy products picked up in the United States. Milk from cows not treated with bovine hormone, recombinant bovine hormone. Now that's a fact. They're just saying, and if you want that, if you want to avoid that kind of treatment of cows, fine. But they're forced to put under this label, forced by law, by our wonderful FDA, to say no significant difference has been shown between milk derived from cows treated with RBST and those not treated with RBST. Now, if you're very up on the literature, you will know right away this is a red flag. The literature probably shows no such thing. And for whatever it is, they filled out some studies that got P greater than 0.05 to produce the producers. A special interest group forced a statement of fact to be accompanied by a misleading technical claim to benefit sales. Actually, it turns out to be a false claim, which often these things turn out. Here's when this was being enforced and when they were trying to push for the same thing in Britain, a British group tried to publish using Monsanto's data, then the data on the trials, 8 trials. They found an increase, and it's only 19%, but an average increase in somatic cell count, which is pus, in milk from cows treated with RBST. They're generating more milk and they're getting milk harder, and as a result, they're getting more infections and they're getting more pus in the milk. And here's a forest plot for that. And in reality, 5 of the 8 of them are not statistically significant. And I have been in hearings where the industry will argue, the industry lawyers will argue, you see, most studies don't find anything. This is what it means when you see this there's no significant difference. But of course, if you did a meta-analysis, you would immediately see there is a difference. Not only that, but all but one of them, only one of them is below 1, and that in itself is significant. Another way this manipulation takes place is the replication crisis. I'm sure you've all heard that title. It's constantly portrayed as one of perverse incentives to make discoveries by searching out statistical significance, producing publication bias. And that It's true, it does go on. It goes on like it has been going on for decades in fields like experimental psychology. Just turn that into a rubbish heap. Lowering significance thresholds, which has been recommended as a temporizing measure, if not a curative for this, only increases the bias, only makes it worse. But any selective publication based on outcomes damages the literature. And yet defense and promotion of significant selection continues unabated. And you can read about that. You can read the defenses going on about that, how editors still see to this day, need a basis for deciding on whether to accept studies. More subtly, their standard story ignores the perverse incentives to find and report negative results by upward p-hacking or by misreporting ambiguous results as negative. For example, when researchers, sponsors, and editors want to dismiss undesirable associations, or when replication failures are more publishable than mere replication. Once there's a controversial set of studies that have found an association, you can get more traction publishing in places like JAMA by getting a negative study, which means p greater than 0.5, or both those things going on. And here's an example. People say, why do you keep using this example? Well, because I know the detail, the backstory behind it. I know what was going on here. The association, but here they're looking at SSRIs and autism spectrum disorder, ASD, in the use during pregnancy. Here is from what they show in their abstract. What their protocol, as a protocol called for Cox model, proportional hazards model, they get an adjusted hazard ratio of about 1.6 with a confidence interval running from about 1.2 to 2.2. Notice I'm going over the false precision here. Then they say after inverse probability of treatment weighted HTPS, these are so sophisticated fellows, the association was not significant. And what do they have? They still got a hazard ratio of 1.6. And now they give it to 3 digits, 0.997, the lower limit. The P is 0.505. So the abstract and article concludes in utero exposure was not associated with autism spectrum disorder. Now, I regard this as, shall we say, prevarication. Articles decrying this sort of misreporting date back to Carl Pearson, 1906. Look what he said. Absence of significance relative to the size of samples is too often interpreted by the casual reader's denial of all differentiation, and this may be disastrous. This has been, warning has been repeated over and over again since then. Why does it continue in such naked forms? Is it mere ignorance? No, my hypothesis, as I've witnessed, is forced by JAMA to protect industry against litigation. Here we have another 1931. When we fail to find any statistically significant differences, we are not justified in concluding that no real differences exist. Now, let's look at background. How about we put some context in this? Well, they actually had a meta-analysis, same group, which had 4 earlier cohorts, which got hazard ratio 1.7, limits 1.1 and 2.6. But in this new paper, they did not, which got in JAMA instead of wherever this was, especially journal, they did not attempt to combine their new study with those studies. Then they did not even cite a 2016 meta-analysis of 16 cohort studies that got hazard ratio of 1.7, with again, interval from 1.2 to 2.5, plus 5 case control studies running a little bit higher. Why no discussion of the consistent association of 60 to 70% higher risk among the exposed? There wasn't any. It's over and over again. You get the same thing across these studies. The variation is right within random, random effects, fixed effects model will give the same thing. No discussion of it. You have to think about that. Well, the reason is because there's certain, most everybody and the editors, they want to say this highly replicated association is pure confounding. And then they report other studies, observational studies. Obviously, they have to be observational. Observational studies are derided and denigrated when they don't come up with the answers people want. Well, it's just observational. But when they're coming up with the answers people want, well, they just say it's it's fine. And then they'll say, well, the association found in previous studies, and by the way, they don't reference anywhere near most of those previous studies, is likely due to confounding factors. I can go on in detail. I can argue that, I guess, but I want to talk about the dominant social bias. Is to talk as if all incentives are discover rather than refute effects. It's a meta bias rampant in the replication crisis literature, which critically ignores differences in incentives across topics and authors. And the Brown et al. Example has the appearance of CI hacking increased width by adjusting the confidence interval until it finally includes 1. Even though that has the appearance of over-adjustment, inflating variance without removing bias. Now, it turns out some inside information is that one, if they had applied the update released at the time of that study to that HTTPS software, there was an update released. It was an improvement in the precision, and it would have pulled that lower limit above 1. And by the way, they had been sent that update. Now, again, I'm not saying the SSRIs cause ASD. These are all associations, but the point is that spin is the driver through the garden of forking paths, a phrase due to Gilman and Loken. Objective statistics are perceived, selected, and reported based on preferred causal stories and in high-stakes settings, political and litigation concerns. Examples abound throughout the health and medical sciences. I can pick up the journals, and if I get into if it's a topic I know about, this is why I said the saddest part. All I have to do is read the authors, their location, the title of the paper, and I know what they're going to say. If I know about these authors, I know what if they've been prescribing this drug, I know what they're going to say. Statistical training and any training that pretends otherwise obscures and fosters that manipulation. So the causal stories that we want believed causally affect analysis choices and output interpretation. And the result is that reports often function as lawyering for those stories, which a major source of blindness to the problem is the pundits and meta-research neglecting their own cognitive and political biases and training deficiencies, as well as deficiencies of developers, instructors, users, and consumers of statistics. We've got one of the biggest problems in that regard. And I go, he knows what I think of it. It's a certain Greek fellow at Stanford who I won't name. Here, the issue is this romantic, heroic fantasy science committed to fact-finding and dissemination of valid facts regardless of the social consequences. This is a romantic fantasy that I held. I was raised with some kind of notion of objective science, but almost no one would disseminate all valid facts regardless of the consequences. The harsh reality is that much of statistics serves commitments of major social networks to warp portrayal of facts into propaganda, to direct society according to the network's valuations and special interests. You saw that very clearly in the labeling of dairy products. And what I'm saying is that I find it's just rife throughout the medical literature and what determines medical treatments. An example is the endless promotion of randomized trials and gold standards when they are no such thing, due to, as we as epidemiologists know this better, it seems, than most people. There's a lot of economists that are starting to rebel too, I've noticed online. Huge generalization bias in randomized trials due to exclusion of high-risk patients on ethics and liability grounds, and placebo formulas that vary across the trials that have real side effects. Turns out a lot of these placebos are not inert. Numbers are too small and follow-up too short to discern adverse effects, resulting in non-significance reported as replication failure. This is rampant. They're always saying, you'll see all this stuff, all these articles saying how this was refuted by trials. This observational study was refuted. Epidemiology was refuted by randomized trials. You go to the trials, they couldn't refute anything. They couldn't refute Martians controlling all of us right now. Hidden protocol violations plus selective publication, reporting, and discussion. Here's a typical example. I promised you, Sheena, that I'd give you a COVID example. Here's a randomized trial just published, ivermectin to prevent hospitalization in patients with COVID-19. Just published in Biomed Central. Abstract. Okay, look at the numbers. Odds ratio 0.65, limits 0.32, 1.31. That was reported as ivermectin had no significant effect on preventing hospitalization. And then posted online a tweet over this, talking about, this ivermectin literature is It's beautiful because it's insane. There's all kinds of studies in it that are just, look, absolutely nuts. And there are studies. This one is a much more dignified presentation that made it into a decent journal. This one is, although they're all done for some reason in almost all of them in developing countries. Well, I don't know if you call Argentina one, but this is an example. But this post was slamming the ivermectin trials and the meta-analyses that have just come out. One of the studies in those meta-analyses just got withdrawn. Looks like it was obviously fabricated. It does not mention, though, that this result, but wrote it found no benefit for ivermectin on death. But if I go to page 5 of the Vallejo study, they only mention in passing in the abstract, I see that the odds ratio for death is based on 4 ivermectin deaths and 3 placebo deaths. So what do they get? Odds ratio 1.34, confidence limits of 0.3 and 6. Now, what does this show? What are these results? Can we say, should people be saying ivermectin, touting this study as this study found no effect? This is now being touted as saying, we have another negative study. This study was too small to find anything. It doesn't show anything. It's a typical randomized trial that you see in the medical literature. It is so small and noisy that it's consistent, that it doesn't rule out anything but the most extreme claims, which none of us who are willing to give ivermectin a chance and believed. I mean, yes, there were some claiming it was a 5-fold reduction and so forth, but 0.3 is a really important effect. And if you appreciate how liberal what's the right word? Well, how narrow these confidence intervals are, because the 5% level is actually very little evidence. It sounds like it's small, but we'll get to that. You appreciate that this trial, typically of almost all these trials, didn't show anything. It was too small to show anything. The only way it's going to contribute anything to the extent it's legit is to be combined with all the other little trials in a meta-analysis. Here's a survey from MedPage today, bait and switch and IBD trials. Primary outcomes often go unreported or change midstream. So there's supposed to be rules that have come in to prevent problems of publication bias and so forth, and enforce protocols. So here, analysis of 57 phase 3 trials with published results indicated that half either never reported at least one of pre-specified primary outcomes, or at least one of those outcomes was changed without explanation. Other studies have found many registered trials are never published despite stated intent to do so. Why is that? I'm sure there's a universe of reasons as you go across them. So going through all this, although I read the cognitive biases literature decades and decades ago, it started coming out when I was a student, I really came to appreciate this empirical fact that Tversky of Kahneman and Tversky fame comment on. My colleagues, they study artificial intelligence. Me, I study natural stupidity. We are all stupid, if not corrupt. Even if we're sincere, we have massive cognitive biases and blindnesses. As he said, whenever there is a simple error that most laymen fall for, there is always a slightly more sophisticated version of the same problem that experts fall for. And the classic example is interpretation of p-values. We laugh at people when they say p-value is the probability of the null, but I see experts all the time saying things like, they're trying to explain a p-value. I say, well, it's the probability chance alone produced the association. Chance alone is the null. This is basic logic. If you say it was chance alone, you are saying there was no effect and there was no bias. Just think about it for a minute. And yet you'll find this in all kinds of discussions, this kind of interpretations, or one just like it, and by experts, by people who are celebrated professors of statistics with all kinds of publications in like the Annals of Statistics and Jazz Theory and Methods. For the longest time, and I still do, I think, say everybody, if you're going to be studying statistics, you should understand Bayesian statistics because frequentist statistics are incomplete and Bayesian statistics are incomplete and they're complementary. But people started calling me a Bayesian. I said, I'm not a Bayesian. Don't call me a Bayesian. That's just calling me a member of another religious sect. Bayesian methods open statistics to even more abuse via prior spikes and elicited priors. summary, the listed priors are summary expressions of biases, literature misreadings, and prejudices, like the ones I just gave you. An example, whenever you see these things about Bayes factors, and they've been promoted in the medical literature by intelligent, very smart people, claiming they use the idea that the null is 0.5 probability, and they call that indifference. That's not indifference, that's massive null bias. Just think about what kind of randomized trial, how big a randomized trial would you need to get a spike right on 0.5? I know, I don't think many of you could think of that, but I assure you it's like nothing you've ever seen. And here's something from Kahneman, his co-author. This is most relevant. Illusions of validity and skill are supported by a powerful professional culture. We know that people can maintain an unshakable faith in any proposition, however absurd, when they are sustained by a community of like-minded believers. Just see any defense of significant system. That's how those look to me, like a lot of very involved, clever, extensive, rationalized double talk that has really not just logically incoherent, because this has to be maintained. The practice that has been done in the past, that is enshrined in articles, textbooks, practice, consulting, has to be maintained. How are you going to shake that? You might as well try and shake the grip of a religious sect on certain segments of government. Because it is the same. Any instruction purporting to cover the basics of inference and needs to include cognitive science. This is, I want to get to my instructional views that deal with social delusions and biases such as nullism, which is the confusion of our need for parsimony or shrinkage to zero. I'm all for shrinkage to zero when it's called for, but you don't want to confuse that with reality. Reality doesn't care about what we are thinking. Dichotomania, confusion of our need for summarization and simplification with, and our need to make decisions with our preference for black or white thinking. The last is a bias. The first may be a need, but the last is a vice. And reification, faith that formal methods for reasoning, inference, and decision suffice for real world reasoning, inference, and decision. Now, some of you may have read or at least heard of Nassim Taleb, the guy who engaged in years of books worth of vicious attacks on economics, precisely because they were doing this, confusing and trying to sell formal methods for real world reasoning, inference, and decision. And he gives a lot of examples of how that bankrupted whole hedge funds. Again, this is against nullism. Reality is under no obligation to be simple or decisive. Dichotomania, that's many, or if not most important decisions should not be binary. Where do you set your oven? Do you have it on or off? Your thermostat, is it on or off? Your medication level. Well, unfortunately, a lot of medicines are only available, or doctors will only prescribe them in one dose, which is an overdose for a huge number of recipients in many instances that I've examined. Hidden reification, this is much more subtle. Researchers routinely publish inferences that ignore the vast model uncertainties. They run things through a package program, which all its confidence intervals, everything that comes out of it depends on all kinds of simplifications and assumptions. And they just don't think about all of them, most of them. Now, my view is that if I was going back to the beginning and teaching epidemiologic methods and statistical methods, I would rebel from the start and start with psychology, cognitive psychology, that kind of cognitive psychology, the kind that discusses cognitive biases, the kind that are operating in me and you and everyone, because we have a hard wiring for these things. What do you expect, sincerely? How do you expect us to be any better if given the way, as I believe as I do, this is what we evolved from. We evolved to use very fast heuristics to save us in an instant of being attacked, for example. This is not what science is about. We have all these problems like anchoring, confirmation bias, courtesy bias. That's one I certainly managed to break. The tendency to be obscure about criticism that will cause offense. Failure to test alternatives, selective criticism, selective reasoning to desired conclusions using selective assumptions, explanations, and data, Dunning-Kruger effects, overconfidence and validity illusions, the tendency to think methods are as accurate in the world about the world as they are in the math, which are thought experiments used to derive it. Familiarity bias, territorial exclusionary bias, that's against epistemic trespassing, groupthink and herd behavior biases, such as repetition bias, well, everybody says, and mind projection fallacies, imbuing inert quantities with attitudes, opinions, values, inferences, judgments, and decisions. That one is rampant in statistical discussions, thanks to using value descriptors. It's encouraged by statistics, like significance, confidence, and severity. Whenever I see these words being used with knowledge that they're being criticized by commentators, I view them as taking part in the effort to basically pull the wool over people's eyes about these things. The top example of the nonsense, p-values overstate evidence. I see this over and over again in advanced statistical articles. That is insane. P-values only provide the position of a statistics in a reference distribution, such as a chi-square derived from a model. Any evidence overstatement is by the viewer. And these aren't absolutely sharp categories, but just heuristic triggers to avoid getting lulled or suckered by colleagues, however well-meaning they are, and experts, and most of all ourselves. And these kinds of systemic problems are major reasons why most published research findings are false. Instead, instructors indulge in all these problems, and observations can never provide absolute certainties and can't even provide accurate assessments of uncertainties. But statistics caters to our cravings for certainty by providing sophisticated decision theories that make it appear to users that observations can provide definitive risk and uncertainty assessments. Like in the abstract I read, confidence intervals, they were proposed, and they were an improvement of just people stating things being significant or not. Rothman fought hard for decades to get confidence intervals part of the standard of presentation in medical journals and epidemiologic journals, and he succeeded. He and Altman and Bland and others campaigned for this for decades, and they succeeded. What happened? This is what happens, unintended effects. Confidence intervals perpetuate these illusions by deceptively appearing to capture all the uncertainty sources in applications when the only uncertainty they capture is that given the model used to compute them. And when our models are wrong, and they all are wrong, don't ever think otherwise, then they're not capturing all the uncertainty. They're not capturing all the bias, all the problems, all the measurement error, everything that we can think of as good epidemiologists. And worse, the standard presentations rarely mention their neglect of those uncertainties, like those I just read. These problems underscore the need for coverage of causal reasoning errors and cognitive biases as essential component of any specialty claiming to promote sound scientific inference. And in doing so, we have to talk about value bias, because that pervades statistical methodology in the form of nullism. Value is biased towards accepting the null. These biases are usually obscured from public recognition by adherence to statistical traditions and mathematics that hide the values and obscure cost-benefit assumptions in null hypothesis significance testing and Bayesian analogs. And the consistent use of the null as a test hypothesis is an example of that. So I will skip over some of these. So I want to mention that multiplicity adjustments, which are vehemently pushed by some statisticians, worsen value bias. They take a joint null as the hypothesis, and their treatments basically says it's more important to not reject that joint null incorrectly and apply the same type 1 error rate, apply it to the entire ensemble of nulls. What they're assuming is that false positive costs are always more than false negative costs, and that these cost ratios always increase with the number of hypotheses. This valuation does apply to drug companies monitoring adverse effects, but it does not apply to patients. It does not apply to you and I. We don't consider missing a serious drug side effect to be something any less serious than accidentally thinking there's a drug side effect. And as I mentioned, this about prior spikes. So I'm going to skip some of these. By the way, there was a recent survey relative of verbal definitions and descriptions, and p-values and significance. And this was done in psychology literature, but they found about 90% of introduction to psychology textbooks that define or explain statistical significance do so incorrectly. And I have one large psych text on my shelf that I pulled off when I saw this thing, and I looked it up, wasn't in their survey, and I looked it up, and sure enough, it had a completely wrong definition of p-value. Well, so here's an easy step towards reform. Let's start out at step 0. Teach that data transforms are all that statistics can supply. Examples are p-values, posterior probabilities, and interval estimates. All those are stuff that comes out of slapping algorithms on data, transforming the data in some way, and spitting out a number. That's what's being done when we analyze data with our programs. We, the observers, and others who are looking at it, supply meaning for the statistics via our causal models of the physical research reality. Justified statistical inferences thus require showing how statistical assumptions can be derived from the physical research reality. How often do I see studies do that? Even if I look back on ones I've been on, just about very little in the direct form, but and I think and I certainly do, when I think of a good study, I see them list out everything that they were doing in detail so that I can at least figure out whether there is some justification for the statistical model they're using. And then once we do that, we show where the data fall relative to what the assumptions taken together predict. And that's what a p-value is. So here's a reform step to take it as step 1 as opposed to step 0. Extricate p-values from the dung heap of null hypothesis significance testing. Both critics and defenders of significance testing misidentify p-values with their traditional use as insignificance testing. They were even called significance levels in much of the, especially English tradition, British tradition, stat literature I was raised with. This is a confusion. It's like calling all knives weapons. It's a confusion of a tool with its misuse. And it's precisely using p-values to murder thought. It's destructive because p-values can be used instead for many tasks divorced from significance testing. For measurement of model fit, for one thing, is estimation devices and building logical bridges between frequent distribution statistics. But if we rehabilitate p-values, and even if we get rid of the dichotomania, dividing them and significance terminology, we'll still face that instructors and users want p-values to be the probability of the hypothesis that's supposedly being tested. And a p-value is usually not near that probability. Yet, again, teaching and research literature encourages subtle, fallacious verbal descriptions that are equivalent to teaching p as if it were the hypothesis probability. And the literature is filled with botched descriptions, as I said. I'm not going to go through all these examples that I've talked about before many times. So I'll just continue with the idea of reconstructing statistical training to stop perpetuating mistakes of the great men of statistics, the traditions, the destructive traditions, and the cognitive biases they displayed, created, and encouraged. Those statistics texts assume instructors and students understand logic and semantics to see through bad terminology and discriminate mathematical from contextual meaning. As shown, by the time Fisher burst on the scene in fame in the 1920s, there were already complaints in the 19-teens about confusing statistical significance with practical or contextual or medical significance. And it only got worse after Fisher. Now, one thing that I want to emphasize, I would like to emphasize shifting away from conditional hypothesis testing interpretations to unconditional descriptive interpretations of statistics. The norm is the p-value is the probability of getting a test statistic as or more extreme if the test hypothesis H is correct. That leaves the background assumptions in the model, that is, implicit. Instead, bringing assumptions forward when you talk about them, when you report results. And we recognize that a p-value is the percentile at which the test statistic falls under the test model. The test model includes the test hypothesis and all other assumptions used to compute the p-value. Wrong direction. Here's a graphical attempt to show what I'm talking about. The tradition is on the left, traditional. we make this whole big circle of assumptions on the left with those red things left in the background. The only thing that we use all those things in that big circle to deduce the p-value and the confidence limits and so forth. But then we only focus them back on the test hypothesis. If something looks off about them, we say, oh, the hypothesis is off. Or if everything looks fine, we say, oh, nothing, no association was found, which is basically like accepting this hypothesis for a lot of writers. What we should do instead is make sure that we have in the foreground everything that is involved in the deduction, all the assumptions, the assumed distributional form, that the assumption that there's no uncontrolled systematic errors, other assumptions like that everything is log linear or logistic linear or proportional hazard. And the test hypothesis is just one of all those assumptions. Most analyses try to refute the hypothesis, but the p-value is computed from a test model containing many assumptions. Deconditioning means emphasizing that violations of any assumption used to derive the p-value can be responsible for its size, not just violation of the test hypothesis. Now, good writers know this. They write intuitively, knowing this, understanding that their results could be from other reasons. But that's not how it gets picked up by the editorials I read in the medical journal and in medical newsletters, and then in the popular press. Large p, like small, it does not confirm a hypothesis or the test model. Absence of evidence is not evidence of absence. Part of this program too is to overthrow misleading traditional jargon. I call it stat speak in deference to Orwell newspeak, to realign statistical terminology with ordinary language. Most users must depend on ordinary language descriptions, replace significance and confidence with compatibility, measured by the p-value, as it ranges from 0, no compatibility, to 1, full compatibility of the data with the test model in the direction measured by the statistic. Why do that? Because for most users, the mathematics are simply symbolic incantations they must take on faith to get funded and published. Now, I get attacked here saying, oh, that's just semantics. I'd say that's the height of irresponsibility. It fails to grasp the essential analogical information conveyed by the meaning of the words, the semantics. That failure is common among the mathematically able who place syntax and deduction above analogical processes or dismiss or overlook the role of analogy and mapping between reality and map. And they love to overlook context. Stop repeating Fisher's error of using null hypothesis for any test hypothesis. It's amazing how statisticians cling to this one, if they were, especially if they were educated in the British tradition. It's an error which openly invites holistic bias. Null in English dictionaries, whether British or American, it means having or associated with the value 0, it means 0, related to 0, it means nothing. It's not, that's what the ordinary English meaning is. Any hypothesis that is not that something is 0 or translated to that in a straightforward common sense way is a misuse of the words. Instead, use Neyman's term. Neyman recognized this because English was, probably because English was his 4th or 5th language. He used the term test hypothesis to emphasize testing directional, non-null, and interval hypotheses instead of just point null hypotheses. But then Neyman get rid of his confidence trick. He's the one who started talking about confidence intervals. Assigning high confidence is not distinct from assigning high probability. Here he was basically trying to sell his interval estimation approach to an audience, which at the time included many old-style inverse probability Bayesians. So we name and reconceptualize CI as compatibility intervals showing parameter values found most compatible with the data under some compatibility criterion. That's going to be somewhat arbitrary, but this is sometimes we have to make sacrifices to save space. And this involves no computational numeric change. It's all about perception, thinking about user perceptions, including ordinary physicians, including medical editors, including science reporters, including newscasters. Compatible is far more cautious and logically much weaker than confidence. There's always an infinitude of possibilities compatible with our data. Most are unimagined or even unimaginable given our knowledge. We should recount the dogmatic denials by great men of what became accepted facts. Confidence implies belief and encourages the inversion fallacies that treats CIs as if they were posterior intervals. I emphasize that compatibility, this is no basis for confidence. False stories can be compatible with data and lead to effective interventions. The classic story, malaria is caused by bad air that collects near the ground around swamps. This was believed for centuries. The implied and effective solutions, raised dwellings on stilts, drain swamps. It's compatible, cause bad air, and the actual cause, mosquitoes, are both reduced by those interventions. But if we were confident in the story, if we cling to it, just like people cling to significance, it will eventually mislead, and it has misled. That story, the original story, bad air leads away from the use of mosquito nets. Then they say, well, confidence intervals are about coverage rates. Well, those coverage rates are purely hypothetical frequency properties, which we should have no confidence, especially in observation studies, but even in most or many randomized trials that I see. Confidence requires us to know for certain that the actual relative frequency with which the interval will cover for the generator is as stated. But if we don't know the actual data generator in detail, no such confidence is warranted. Stated coverage just only refers to repeated draws from a hypothetical, idealized data generating algorithm that we're not observing, not to the causal story that we'd be sure of. Its compatibility is merely an observed relation between data and models. So here's an honest way to write a report. The Brown study, the association of SSRIs with ASD in utero exposure. Here's how the abstract could have been. The Cox model adjusted hazard ratio was 1.6. The 95% compatibility limits were 1.2 to 2.2. Using IPTW HTTPS, the hazard ratio estimate was much less precise. And there it is. Confidence limits 1 to 2.6. Conclusion, under our HTTPS model, up front, the data appear most compatible with associations ranging from 0 to a 2.6-fold elevation of ASD in children with in utero SSRI exposure. This is not claiming anything like what they claim, no association. No association is right on the edge of what we consider the most compatible. Here's an honest report of the Vallejos study, ivermectin. Hospitalization odds ratio was 0.65, 95% compatibility limits were 0.32 to 1.31. Mortality odds ratio was 1.34, limits 0.36. Conclusion, the results were too imprecise to determine the size or direction of the effect. Being most compatible with hospitalization odds ranging from 68% lower to 31% higher, and mortality odds 70% lower to 500% higher in the ivermectin group compared to the placebo group. How many studies have you seen reported in any journal or major journal that they said, we can't conclude anything, sorry? Do you think they would have gotten published then? They didn't think so. And they're probably right. So this is part of the systemic rot. And statistics is being used to promote this kind of rot, the rot of what was reported as if they had a conclusion. They have no conclusion. The study was too small. That does not mean it wasn't worth reporting. We need to see all the data. The worst thing would have been, and at least that wasn't done, was have this study rejected because it wasn't significant. But a negative study of ivermectin, and by negative, I mean P greater than 0.05, is more publishable in a leading journal right now today than a positive result. That is an opinion of mine, which I've seen played out. Stop repeating the error, massive error of not treating p-values as estimation tools. That is all falls into that. Look at p-value functions. To get a picture of all this, all I'm talking about, here's from the Brown study, the SSRI and ASD study. There's their p-value function. Now that's assuming their inverse probability treatment weighting model. And you can see right there, a test for doubling of hazard. The hazard ratio of 2 yields a p-value of 0.37. That's a much higher p-value than the 0.505 that you get for a hazard ratio of 1. Now that's not something, that's something I don't think their handling editors, reviewers, or the authors wanted anybody to notice. And it's a fact. This study is mainly concentrated in, like all the other studies that were reviewed, above the null. again, that we know it's an epidemic. It doesn't mean it's causal. These aren't randomized trials, but this was actually an excellent epidemiologic study by our usual standards. If I look closely at the methods, the problem with the study, and I see this over and over again, I'm not picking on something methodological in its conduct, except the analysis and the present, and really, especially the presentation. The presentation of the results is the last bastion of scoundrels, where everything can be done right up there and say, everybody say this was a fabulous, excellent study, and therefore give credibility to a complete misinterpretation given at the end, that the study found no association. And that's how it was reported throughout the medical press. It did not find no association. It found the same association every other study had. Okay, I'm sure I'm out of time, right?
Yes. Very much so.
I could go on and on, but I will stop there. Except I'll just go to the next slide. I want to translate to S values. Now, what I'll do is I'm going to linger on so that people will they can get on their screen when this recording is posted, some background reading. I'm going to leave that up a little, and then there's another page of articles. Almost all these are open access. I think they all are. Go ahead.
Okay, great. Thanks very much, Sander. Do you mind muting yourself? There seems to be some echo. Thanks. So we have gone over time. Sander, are you happy to hang around for a few more minutes if people have questions? That's all right. Yep. Okay, so if you have some questions, you can either pop them in the chat or raise your hand, although we might have trouble keeping track of who's raising their hand. So I guess one of the salient messages for me is that every time we reform epidemiological teaching, we try to focus on including more and more about methods, but it seems like now we have to reform it again to include cognitive science, and probably not cognitive psychology from what you've said about psychology textbooks. Anyway, so I can't actually easily monitor the hands. So Alison and Shuai, if you see any hands going up, please let me know. But if anyone does have a question, okay, people are putting them in the chat. All right, so people have said, thank you for making us think, Sander, and thanks for a great talk. So Faheen has asked if you can please comment on the use of effect size, please.
What? On what?
Effect size. The use of the effect size as opposed to
using the effect size. I'm not sure I understand the question. Using effect size for what?
Faheen, can you provide a bit more info?
I'm not sorry. Maybe it's because it's past bedtime.
I guess the context in which it's used is when doing sample size calculations, there's an emphasis either on some level of statistical significance or some expected effect size. So would
yeah, I'm as far as I'm concerned, this I prefer the approach and have for decades. I had an article in 1988 in the American Journal of Epidemiology on doing sample size calculations for using confidence intervals. And then Rothman and I published an article on that, a simplification basically of that idea, since that mine didn't catch on a few years ago, and published that in Epidemiology, or I think it was, so that we shouldn't be focusing on these scientific outcomes. We're saying we want to narrow things down to a certain level, of precision. This is something that is actually done in a certain branch, specialty, very extreme specialty of statistical hypothesis testing. There's an irony here that null hypothesis testing, NHST, which I revile and everybody should, is actually a distortion or a special case, a misleading slice chopped off of a very general set of procedures that includes things like equivalence testing, superiority testing, non-inferiority testing, and so forth. And in those topic areas, you have this idea, also minimal effects testing. And in equivalence testing, you actually could calculate, or in effect calculate the sample size narrow enough, sample size large enough so that you can get a confidence interval narrow enough so that it could conceivably narrow things down to the extent you want. The problem is trying to dictate, letting too much what you want as an outcome dictate what you're going to do with the study. And the ideas instead should be, how much information are we going to get out of this study? How much, for the money that is going to be spent and the effort and so forth, and the risk perhaps to patients if it's a trial, what is the value added that we'll get out of this study? If all we're going to get out of this study is the ridiculous confidence intervals that we saw with Beleos, if this is what we're going to get out of it, was this worth its cost? I don't know what the study cost. And maybe it was, because people have asked things, what's the cost per patient? But I think that's how we should be thinking of it in terms of its potential to answer questions. This study from the get-go, people would say it's underpowered. Now, I don't like that term because it brings us back to NHST, but it does capture the idea that the study wasn't really going to be capable of settling anything. Now, if the study was practically free, if it was done for, let's say at a minimal cost, if this was a few thousand, it was worth it. It could go into a meta-analysis. If this cost $20 million, no, it wouldn't be worth it. Perhaps not. I'm not saying, but I'm just saying, this is how I would think of it.
But aren't we sometimes interested in a meaningful effect? Aren't we sometimes, do we think, for example, that a 30% increase is a good thing and good enough to justify the cost in this particular situation where, perhaps it's saving a large number of lives or saving a large number of hospitalizations?
Well, how are you going to know that if you have a result that's all over the board? What if the mortality odds ratio for ivermectin given early, probably the way the proponents pushed it, what if it is 0.3? This study certainly doesn't refute that idea by any stretch. It's this randomized. If in that S-value slide, the stuff I'm not covering, once again, never getting to, that 0.3 represents about 4 bits of information. That's like 4 coined against that idea. It's 0.3. In other words, hardly anything. In other words, this leaves on the table what looks to me like a very large clinical effect for an incredibly cheap drug. But of course, I live in the US where the FDA requires that drug to be new and cost $50,000 per patient before it's going to approve it, over the objections of its advisory board of people who might be thinking like me.
The conclusions of this study, so your conclusion is that the results were too imprecise, and the conclusions of the authors were probably more along the lines of there's no evidence to suggest. So then is the wording also important? So in terms of changing people's mindset, is the wording in our conclusions important, that there's not evidence to suggest or there's strong evidence to suggest, rather than saying it was statistically significant, it had an effect size that suggested it was statistically significant?
Well, again, I'm not following exactly. If you wrote down, there's many other ways the conclusion could have been written, and I wrote a conclusion there that I would think, oh, that's good, as opposed to what the authors stated as their conclusion. Same thing for Brown et al. Brown et al. Said there was no association. What can I call that? It's a lie. It's a lie. That's all. But it's a lie they believed. It's a lie they believed because they don't want to believe that there's an association you can't get rid of. By the way, that ASD, the SSRI and ASD, this topic looks very close to what at least to how it looked 20 years ago when I was involved in the household electromagnetic field exposure and childhood leukemia. Very similar results, getting results over and over again. They're all clustering in a nice normal distribution around 1.6 or so. Odds ratios in case control studies over and over again with all kinds of different measurement errors. And the studies that got 1.5 got P greater than 0.05 and were touted in the press as saying this association has finally been refuted. And it goes on and on like that. And everything, all the studies were so homogeneous. It's unbelievable. They shouldn't have been that homogeneous. So yes, it's a matter of words. It is a war of words. And we're fighting it because the field of statistics has distracted and hypnotized science with math and numbers. It's the magic of physics. It's like, it's again, cargo. I love what Phil Stark, statistician at Berkeley, and others have used this term, cargo cult statistics. Cargo cult statistics. Now, that would be considered, it's not politically acceptable to say that anymore, but that's the idea that we're going to take these structures that have a very precise meaning and use in the narrow confines of tightly controlled experiments, and we're going to apply them in this world right here of observational studies of one of the most widely prescribed drugs, and an outcome which, if that association was, if there really was a 60 or 70% increase caused by them, the cost of that to society is staggering, because the cost of treating autism spectrum disorder depends on how severe, can run hundreds and hundreds of thousands of dollars when accumulated over the child's lifetime. This is a high stakes topic, and this is how it's being treated. It's all being used, it's all being done as if it's being done by lawyers. The scientists and the statisticians have become like lawyers, or they're using the statistical technique as if they were arguing, trying to convince the jury of the peers of the research community, and especially the press and the medical users, but really juries, because if they had reported, I know that if they had reported that there was this association reported, it would have been used as a basis to inspire lawsuits as part of it's science. Our science functions in the confines of the society. In the United States, it's a lawsuit crazy society. Anything like that could be a basis for a lawsuit, and has been.
Yeah, so John Hopper's also put in the chat some comments on this issue of power calculations and statistical significance, that, you know, power calculations should be pitched in terms of what size of effect, for want of a better word, are you prepared to miss after spending lots of time and money. So that, you know, relates back to your point, and that people even in those clinical trial grant review panels actually seem to believe that if a study has power to detect a big effect, it will actually find a big effect, and no one dares to pitch their power calculations on small effects. And there's a bit of a conundrum here too, because, you know, ethical review committees will require you to show your sample size calculations and to show that you have a sufficient sample to detect an effect, because it would be unethical to do the study otherwise. So there is still a drive in many aspects of our daily lives as health researchers, where we kind of have to fall back to the dichotomy. And I know you and others published that paper that you had in your list of references a minute ago, the Nature article about banning statistical significance or something along those lines. Do you reckon you've seen much of a change in the big journals, JAMA aside? It's clear they're not on board.
Well, JAMA is the role model and takes the lead for a whole plethora of medical journals. As you know, there's thousands of medical journals, but hundreds in the United States. And, you know, they're a how do you say, opinion leader.
A negative opinion leader, perhaps. But the fight then is not just with the journals, it's also with the ethics committees, it's also with the grant review panels, it's on multiple fronts. So I guess the suggestion then is that if we start with teaching, then maybe we'll see a slower evolution, but may see change in the people who are emerging from our courses and a different way of thinking. And I don't know, I still think there's a bit of a risk that people will just have to fall back into the patterns that are established in order to get their papers published, in order to get their grants successfully reviewed.
They're trapped by the established system. And well, what can I do? But this, this is just a microcosm and a reflection of things going on in society at large, especially in the United States, where basically, as we've seen recently, and that Alzheimer's drug isn't the only example, the FDA has basically become a captive of the pharmaceutical industry, much like JAMA. And they're a major force behind wanting to make sure we preserve significance. And they have their feedback through their experts who are supposedly opposing them, even in some cases. They're not. It's all part of a social control mechanism to try, for example, to keep a lid on lawsuits and judgments, things like that, and also get expensive products approved. Why the heck wasn't there? Ask yourself this. I mean, this makes people say, oh, he's a conspiracist or something. It's absurd. It's perfectly reasonable to ask why, even a trial like this little trial, there's 200 patients per arm, why this wasn't done a year earlier? Why wasn't this? I mean, people were asking about this and pointing to ivermectin as they were with HCQ. They could have done those trials a year earlier. They could have had these kinds of small results out in the US. And where were they done? They were done overseas by, and in a lot of cases, as we know, reading the studies, by people who didn't really have a good idea how to conduct them or even didn't conduct them and publish things. So we have, it's hard to not, how can you be blind to what's really going on here? Statistics, it's the use of statistics, it's treatment, it's discussion in any kind, at least topics of controversy, which is what I'm concerned with, is being driven by the social forces, the forces in the society around it. And they're big. They're big and they're hard to resist. And they synergize, those forces synergize with the innate conservatism, what I call the strictly ballroom effect. I mean, old experts who taught things this and did things this way all their life. There's one who just published a whole book defending statistical significance, the war on statistical significance. And you can just tell it's basically all about a guy who used it in his consulting service all his life. So it's not about to come around. That's life, that's people.
Good to see you using the strictly ballroom as a reference topic. So one of the issues that you didn't touch on, but that may be related. So Don, I'm sorry, Don, I don't know how to pronounce your family name.
Sheena.
Yes, Ankur.
Sorry, I've got a question. Thank you, Professor Greenland, for the talk. I had a question more about the teaching, because I think I teach an entry-level epidemiology subject. And what I see is there's always this competition between students wanting the likable, dichotomous way of interpreting things, but compared to the uncertainty that we're really talking about, highlighting and appreciating the uncertainty. How do you think that particularly statistics and epidemiology teaching together can bring that element right from entry point, the uncertainty in understanding how some of these things operate?
How do I think? Well, gee, I thought I just talked about that. Again, I feel like I'm missing something in the question. I was just explaining how I think they should operate. I think, now, if you want me to say a little more, I could talk about how I think. I mean, none of these ideas are original to me. I say this over and over again. I pulled all these things out of the literature, some of it going back to before I was born, some of it. One item that has been pointed out is that part of the problem is people are not only enumerate, not only do they have trouble with algebra, I'm thinking algebraically, but they also have problems. Even the ones who can be very fluent in algebra can be like, and become statistics instructors, can be very focused on that without any idea of really connecting it well to the real world. And one of the issues that's brought up that in the United States, at least, or especially with its puritanical history, is that people aren't taught principles of probability of gambling, of uncertainty and risk from a very early age. They don't even begin to encounter it, if they encounter it at all in any didactic way. It's not until they get into college, for the most part. I mean, I'm sure some high schools try and teach it and so forth. But this is a sort of skill like arithmetic and basic algebra that should be introduced to young kids. And there are parents who do that. There are programs where they do try and teach their kids. They teach them how to play, raise them with games of chance like Monopoly, where there's elements of skill and chance blended. And so they come to understand risk, that they, even with their best strategy, they could lose by forces that are completely beyond their ability to foresee what's happening, how the dice is going to come up. And to teach that kind of functional probability through games, through fun things, would be, in my perfect world, or a better world, done early on. I mean, literally at the level where you're introducing arithmetic, so that they can see numbers, the 1, 2, 3, 4, 5, 6 on the die thrown. And they would now get the experience of starting to understand basic so-called ludic game uncertainty. And so that by the time they got to high school, where they're learning more history and geography in a more general way, they would start to be able to understand unquantifiable uncertainty, the kind that you have in real business and finance and economics and epidemiology. So that's the problem. The problem is that the way I look at it is that it's like trying to teach well, I can't testify for you, but it'd be like trying to teach me Chinese by the time I got to college. I would never become anything approaching fluent or really understand the nuances or fine points of Chinese poetry if I learned and hadn't been exposed to Chinese from the time I was very young. And does that make sense? Do you understand what I'm saying?
Yeah, it totally does. And thank you, John, for your comment on the chat as well. That's very helpful that it's in that direction.
Great, thanks, Encore. So, sorry, Sander, where I was going with the last comment was that I don't think you really touched on it, but there's a question here from Don Bichandizi about whether, in the light of the concepts that you've discussed, what's the difference between data-driven machine learning and traditional statistics? Can they inform each other? Are there dangers there that we need to be wary of?
Wary of? Well, the way I put it, the original name, and I say the original form, primitive machine learner, in a very explicit, programmable, easily programmable form, was Neyman Pearson hypothesis testing. That was the idea that you could program people on a production line. And this is what Fisher admitted it would be good for and objected to as a general scientific use, because it enabled somebody who really didn't understand the context of what they were doing and the theory very well to apply a mechanical rule and achieve a particular target error rate under circumstances that have been carefully set up and controlled so that this machine learner could function. Now, that's what I would nominate as the first formal machine learner, was the circa 1930 Neyman Pearson hypothesis testing, which, by the way, included hypotheses other than null, as Neyman pointed out, or allowed for hypotheses other than null. Now, every time you run a regression program, you're using a machine learner. After all, what do we call regression programs? Now, a lot of forms of regression, non-parametric regression, so are called machine learners. Statistical learning, elements of statistical learning, a title of a major book out of Stanford. Those are all learners because you can turn them into these programmable algorithms, and we do. There are those packages sitting right there on my computer and probably yours.
Indeed. So I guess on another topic as well, Ezekiel was asked about the issue of how data are analysed but not necessarily used in clinical practice. And so the specific example is that in statistics, we log normalize or log transform our data, but this is never actually done in clinical practice. And so do you have any thoughts on the that problem of, the way that data are reported and not necessarily how they're used in clinical practice? I think that's what you're getting to, but Ezekiel, please jump on if that's a misinterpretation of your question.
Well, I'm not really, again, there's a lot of questions there. I get I'm not clear on them. I mean, I see log transform used in statistical applications in real studies quite often. I have throughout my career. In fact, it was kind of a standard thing to do when I first was a student, because you didn't have log linear models, and logistic models weren't available in packages yet. So you had to take a Y, figure out some continuous Y and do a log transform if you knew it was a positive outcome. So I'm not sure what is being asked of.
So I have had the experience where a typical example is we were checking for plasma D-dimer, and my learning point at that time, that was more than 15 years ago during my PhD, the learning point at that time was that because the distribution is so wide, I was asked to log transform in order to normalize and the blah, blah, blah. And the point I raised was, hey, this research I am doing is targeting clinicians. What you are asking me to do is not what we do in clinical practice. And I came onto this point, like I'm saying, more than 15 years ago. I came onto the PhD with about 15 years clinical practice on my back. So that is why I'm asking this question. When there are statistical practices that are used to determine what should be reference range or what should be normal range for certain parameters, whereas those bases of definitions are not applicable in the clinical practice.
You know, you are talking about I think, to the extent I understand what you're saying, you're talking about a narrow technical topic about how to analyze data. And to be honest, this is one of the strengths I've seen in some statistics books. There are a lot of really good statistics books. I mean, I'm a huge critic of statistics, especially basic statistics, the way it's taught and the way they send users off to use it. And this may reflect a problem with that. But there are, especially in engineering statistics, I've found a lot of books. Well, engineering statistics, no surprise, because if they screw up, the building falls down, the plane crashes, and so forth. They're held to a much better standard than medical practice, where you can kill 100,000 patients in the span of 5 years and still make a profit. You don't, and there they talk all about things like data transforms the data and how there's things performance. It's all kinds of techniques for transforming, for getting basically the kind of accuracy of answer that they need out of the data, or understanding when they can't and what that kind of data they have to get. It always struck me as much more guided by sense. One of my favorite statistical writers that inspired me, and I took a lot of stuff from, I quoted from sometimes when I've given versions of this talk, is George Box, who was an engineering statistic, famed for that, the Box-Cox transformation. And likewise, D.R. Cox, who's another one I learned huge amounts from his books. His many books was mainly focused in experimental statistics, but especially in physical sciences. And there you have a real hard validation point. Whereas it's been pointed out from the time I was a student, it's pointed out that in medicine, people can get away with basically dissembling for their whole career about treatments. And they can be encouraged and supported in doing so by a whole body of fellow experts. And this has become true of a whole segment of statistics, especially the segment of statistics associated with this field, with medical statistics. So this is, again, I'm focusing on a social problem. You're talking about a technical problem, which you may want to go look at textbooks in fields like engineering statistics, to get some better insight on than what you might have been getting. I don't know what you've been reading, but if you haven't looked over there in those kinds of fields, I recommend that.
Thanks, Sander.
Thanks, Sander.
So we've run over time, but John Hopper, you had one last question in there. Did you want to, you've put in a few comments. Did you want to ask your question as well, or are you still listening? The numbers are dwindling, so.
Yeah, I'm fascinated by why the word study population is being used now in epidemiology papers to describe the sample. I mean, epidemiologists take statistics and just turn it upside down and use the statistical terms as they like. What's behind that, Sander? Why has that creep happened?
I don't know. I was always against it. I would always change it when I was on a manuscript where somebody used it.
It must be being taught somehow. I mean, but it's much bigger issue.
You'll find it in books, for sure.
The epidemiologists never really talk about the population they're actually making inference to. It should be a heading in the papers, but it's not. And of course, it's often a very vague concept about which population you really are making inference to. If someone does a study in Portugal where you think it's making inference about Portuguese, but if they do it in the United States, it's obviously...
Well, there is a big literature on that topic. In modern epidemiology, we tried to be clear about the difference between a source population and a target population. There was the population as the source of where we're getting our subjects, and there was the target population and so forth. But since the third edition of modern epidemiology in 2008, there's been a whole explosion of literature on transportability. It's a sort of a focused version of what we used to call generalizability. And they talk about, they build models for transporting. You have a result in this group. How do you transport that? How transportable is that result? What do you have to do to it? How do you have to massage it to make it seem applicable to another group, population, or whatever over there, over from Portugal to Brazil, or whatever it might be. So if you haven't seen that literature, it's quite a bit of it now. Some of the names associated, Elias Barenboim, one of Pearl students, leads on that along with Pearl, Eric Chechen, Steve Cole, Elizabeth Stewart. Those are some of the names, authors on some of the papers that I've seen on this topic, and they've taken it quite a ways. And I see more and more papers on that now spreading into the econometrics literature, economics literature, and other fields, sociology. So if you haven't looked into that, maybe you'll be heartened to see that people have been attacking this problem and aren't talking in the loose way that you're complaining about, which I always objected to as well.
Thanks for that.
Thanks very much, Sander. I think we should probably leave it there since we are half an hour over time, and I think people have been dropping off at the hour and the half hour, no doubt, to go to other meetings. But thank you so much for agreeing to give this talk. I know it's now 7:30 p.m. Where you are in LA. So, but yeah, thanks very much again. For those of you who are AEA members, the seminar will be available on our website. And are you able to provide a copy of the slides as well, Sander, that we can put on?
I'm happy to. Well, what I'm going to do is I'm going to give you the whole big slide set from the 3 series talks. It's you'll see it, it's 3 hours worth, really, at the rate I go. But right. do let me know when you've got the talk up, the video up. Are you to try and put it on YouTube, because that's much more accessible?
Well, we can certainly look at the options. But no, that would be great. Thanks very much. So yeah, so there's a full gamut of these talks, and Sander's given talks and variations of this at a number of different fora around the world. So, well, from his home, but around the world.
I used to be around the world.
Yeah, it used to be around the world. One day we will be able to travel again. We're not even allowed to leave the country at the moment, so you're at least better off than us. But anyway, thank you very, very much, and thanks to everyone who stayed for the long haul. And I guess the salient lesson for me is that next time we ask you to speak, we'll allocate a lot more time.
Thank you.
All right, great. Thanks
a lot, Sander.
Thank you.